All right, everyone, welcome to another episode of the TWiML AI podcast. I am, of course, your host, Sam Charrington, and today I'm joined by Auke Wiggers. Auke is a research scientist at Qualcomm. Before we get going, be sure to take a moment to hit the subscribe button wherever you're listening to today's show. Auke, thanks for joining me and welcome to the podcast. Today we'll be digging into some of the work you and your colleagues are presenting at ICLR, and especially your work on transformer-based transform coding. But before we do that, I'd love to have you share a little bit about your background and how you came to work in machine learning.
Thanks a lot, Sam. Thanks for having me. So I started out in machine learning, I think, around the time that I studied at UVA. So there was an AI course at UVA, which I joined in 2012. And a couple of co-students who were a year higher than me were quite business oriented. And already during their masters, they were founding small companies. And eventually they guided me into their startup, which was called Cypher. And I believe you've actually interviewed some of the original founders. So that's Max Welling, who's a professor currently at Microsoft. And some of the other original founders are still at Qualcomm. Taco Cohen, who has worked a lot on group equivariant networks, and Tijmen Blankeford. And so they kind of talked me into joining their company. And I guess the rest is history, because this startup was acquired after a couple of years by Qualcomm. And I've been at Qualcomm ever since for the past 4.5 years or so, having worked on concepts like reinforcement learning for autonomous driving, and in the past 2.5 to 3 years, mostly on neural data compression using generative models.
Well, let's dig into that topic. Talk a bit broadly about your research into the compression side of things, and we'll dig deeper.
So I think neural data compression is relatively new. I think that the seminal works came out around 2016, 2017. But it's quite a beautiful application of generative modeling, because most likelihood models, in the end, what they give you is exactly what the name advertises, a likelihood for a data point. And information theory tells us that you can then compress that data point with a certain number of bits. And what these generative models can be used for, and that's how we were applying them, is to estimate likelihood of incoming data points. So you could imagine that's images or audio or video. And using entropy coding, then squeeze out any redundancy, where this likelihood model tells you exactly how many bits you're going to need in order to compress that data. So what we've done in the past couple of years is mainly do this, train big generative models in sort of likelihood modeling tasks, but of course with the end goal that we'll eventually use these in a practical setting. So whereas in typical generative models, you could imagine that big hierarchical VAEs, they train in a fully continuous way, the latent space is continuous. So a big difference in neural data compression is that eventually you have to quantize this. You have to move to integer representations instead of floating points in order to compress in a lossless way. So a large part of the work we've done in the last 3 years is training these big generative models with a quantized latent space. Whereas the general field of generative modeling, I would say, is mostly focused on continuous latent space models.
Mm-hmm, mm-hmm. Often when we're talking about quantization, it's the focus of the conversation is around efficiency and
Mm-hmm.
performance. In this case, we're talking about just the fundamental nature of how you're trying to use the output of the networks for communication.
Yeah,
What's the interplay between the quantization from an efficiency perspective and the way you're using it in compression?
yeah. Thanks for pointing it out. Actually, a good distinction. So in our case, the only thing we need to quantize in theory, as long as we don't deploy these networks, is the latent space. And the reason that we compress this is that this latent variable is actually the compressed representation of the data. So as soon as you want to transmit this to, let's say, different hardware, the only way you can do this in a truly lossless way is if this compressed representation is quantized, because of things like floating point precision, for example. Now, the quantization and efficiency angle comes into play when you think about deploying these generative codecs. So, of course, when we move to device, we would likely want these models to run in fixed point instead of in floating point. But most of the research that we've done so far, leading up to academic publications, for example, has been on floating point models, where the latent space is quantized. And then as soon as we go to prototypes where we deploy these to device, that's when we'll quantize the entire model. So the weights, the activations, and so on. And that's when efficiency becomes most important.
So we've been talking broadly about neural compression thus far and your work in that area, but you've got a particular interest on the video side. Can you talk a little bit about how the work you've done extends to video?
So video compression poses a couple of challenges that image compression, for example, does not. And that's mainly about the subjective experience. So as a human observer, you would want your video to look consistent over time, and you would want the motions to be consistent and so on. And also about exploiting more redundancies. So when you work on image compression, if you want to exploit redundancies, what you'll mainly watch out for are things that are similar across the image. Patterns that appear in different parts of it. Whereas for video, there's also the temporal redundancy. Most of the time, when you look at subsequent frames, they will actually be very close to each other, especially for background of a video, for example. And you can exploit this by making sure that any previously transmitted information, you don't encode it again, so to speak. The other part, so this subjective quality part, makes it a more challenging task, and I think more interesting, therefore, than image compression, as it's very noticeable if you have a codec that produces frames that are inconsistent over time.
Meaning you're watching it and it's jerky and just visually unsettling.
Yeah, exactly. Or speckle noise and those kind of things. So a lot of our research is aimed at exploiting this temporal redundancy, apart from concepts that we borrow from image compression, of course. And more recently, we've also started looking more into how to improve the perceptual quality when you're using this video codec. So that could go as far as GAN-based compression. So when you're really hallucinating parts of the reconstructions that are not truly in the bit stream, but also things like region of interest-based coding. So for example, now that you and I are talking, the background is actually not the most important part of the video. You would want the face to be accurate and maybe text that appears in the video. So paying more attention to that and spending more bits on that is another way to improve perceptual quality.
What's the relationship between the research you're doing on the neural compression side and the historical research that's done into compression pre neural networks? Right, we figured out a lot of these same things. Right, the background's not moving. We don't have to spend as much bandwidth on that. Are you pulling kind of insights from the evolution of that prior work, or is the neural setting so different that you're coming up with new tricks all the time?
I wish the latter were always true. Of course, we're borrowing heavily from domain expertise that's been created over many years, maybe 40, 50 years even. So handcrafted codecs or standard codecs, they apply a lot of domain knowledge that also goes for neural codecs. And what you see most often in especially video coding nowadays is that certain concepts are being pulled in, like this motion compensation that you mentioned. Of course, it's logical to use previous information, already decoded information on the receiver end. So we're borrowing a lot of those concepts from traditional coding. And at the same time, many of the operations used in handcrafted codecs can be replaced in a sometimes more efficient way. And by efficient, I mean from a rate distortion point of view, not necessarily from a computational point of view, than what the handcrafted codecs do.
What are the key benchmark tasks in video compression?
So there are a couple of video data sets that are commonly used for evaluation of any video codec, really. And these have been established by this standards community. The trick is you can't just use any video. You want it to be raw video, as high quality as possible, no compression applied to it. And somewhat counterintuitively, because this is pretty expensive to obtain and store, what most people train on nowadays is not raw video, but actually already compressed video, maybe downsampled or augmented in some way to get rid of compression artifacts.
Okay.
But there are a few common raw video data sets that are commonly used for neural video coding benchmarking.
When you're using these raw video data sets, and then you want to apply the compressions in the real world, say with mobile phone information or camera information, like do you have domain adaptation issues where you have to adapt the work?
Yeah, that's an interesting question. Mostly because there's no big cross-domain benchmark, so it's hard to really judge the impact until you deploy. We did notice this in a few cases, and we have some work addressing this exact issue. So we noticed, for example, when we pre-trained our codecs on some video data set, we test it on some benchmark data set, then we get a certain score. But now if we fine-tune on a subset of that new domain and we test it on some holdout set, we actually see quite a big performance increase. So these neural codecs, they are generalizing beyond what they're trained on. And hopefully your training data set is so diverse that you can handle many cases. But there is room for domain adaptation. And one work of my colleague, Thies, is actually aimed at exactly this issue. So the solution that they come up with is to overfit on the data to compress and then transmit the parameter update, so the model update, along with the bit stream. So what you get is a sort of customized codec for every data point, where the starting point is some global model that hopefully generalizes to many data points. But by altering the model in just a tiny bit, you can gain quite a bit of rate distortion performance.
Another question on the data set, given that a lot of the performance improvements that you're trying to achieve are perceptual, what's the evaluation process? How do you evaluate performance in that environment?
I think the best thing you can always do in perceptual quality evaluation is user studies. So actually having actual people look at the two videos and then judge which one of these two is better by some criteria. Um, and we have some tools to perform user studies. Of course, user studies are quite expensive. So what we typically use until that time are proxy metrics. So there are metrics developed by Netflix, for example, called VMAF, which measures perceptual quality based on some statistics that they observed in their own testing environment. There are many perceptual metrics that we borrow from the GAN literature, such as Frechet inception distance. So these are not perfect. They were actually not really intended for this use case. So Frechet inception distance, for example, uses an inception network pre-trained on ImageNet to extract some of its inputs. So it's not a perfect fit to video, but it's a decent proxy to gauge image quality before you finally do that expensive user study.
So one of the big things that has been happening in this space broadly, computer vision, is the introduction of transformers.
Mm-hmm.
How's that impacted the work you're doing around compression?
So there are actually a few works on transformer-based compression on images, and one of which is the one that we are talking about today. Of course, the work by my colleagues Yang, Yinao, and Tako on transformer-based video compression. And I think the main intuition behind this work is that we know that these convolutions that we're using may not be the perfect building block or basic operator. And we've seen that a lot of the work improving image codecs is aimed at improving the likelihood model. So the model that you eventually use to compress these quantized latents by modeling the distribution. And not a lot of it was focused on changing the transform, as it's called. So the operation that takes the data and then transforms it into this compressed representation. And what Zhang and Yenao did and found out was that you can use some of these vision transformer building blocks in order to create a better transform. And somewhat counterintuitively, because a lot of the transformer and vision transformer models are actually computationally very expensive, they could do so with less computation than with the convolutional models that we've been using up until then. So when they noticed this, that was of course quite a nice insight, and we've been using these vision transformer based building blocks in our transform architectures ever since.
Mm. I don't think we've gone into much detail in the podcast about vision transformers, VIT and SWIN and things like that. Can you provide an overview of how the transformer architectures being applied to vision-oriented tasks?
I think the main intuition behind most modern vision transformers is to treat the image as a collection of patches in a sort of similar way that language transformers may treat language as a collection of sentences, words, tokens. So the typical pipeline is something along these lines. We have an image to encode, let's say, and we would extract patches from that image, embed these in a certain way, and then we just act as if these are the tokens that are being produced by language transformers as well. And we apply these transformer blocks on the resulting vision tokens. Of course, vision transformers were originally proposed for tasks like detection and classification, whereas we're using them in a compression setting. So I guess a big difference between how vision transformers were used in classification and detection and what we're doing is that eventually we have to also generate a dense reconstruction as opposed to a single classification.
Can you talk a little bit more about the research that you mentioned with Taco and his co-author?
Like I said, the key idea behind this is to use this SWIN transformer, which is a type of vision transformer that is more memory efficient than the originally proposed vision transformer. So the vision transformer, as it was proposed, it uses global self-attention, and therefore its memory usage scales quadratically with the size of the image. Now, we most of the time are encoding pretty large images and video, so of course that doesn't really work well. What SWIN transformers propose is to instead use local windows in which you compute local self-attention and then aggregate these windows in a actually quite similar manner to how the early convolutional architectures aggregated information. So you start off with very small windows in which you aggregate almost pixel information. And then at higher levels of the hierarchy, you aggregate whatever came out of those smaller windows. So many inductive biases similar to the convolutional architectures. And because this attention, which is the most expensive operation memory-wise, is only computed locally, it scales linearly with the memory usage scales linearly with the size of the image. So Yang and Yinao figured this is a good fit for compression as well, since we often use very large image and video. And what they did was take a hyperprior architecture, which is one of the seminal image compression architectures, I think originally proposed by Google in 2018, and replace some of the operators, especially the convolution and transpose convolution, by their SWIN transformer equivalent, in order to see, by making a relatively simple change, can we show that these SWIN transformers are better suited for extracting information than convolutions are.
Was it relatively plug and play, or were there some tricks that had to be involved to get it all to work?
I mean, there always are. Some tuning required. But what's nice is that the SWIN codec work was open source. And this is a work by Microsoft Research Asia. And so starting off actually was relatively simple. But yeah, it's largely take the hyperprior architecture and modify it, tune this well, and it turns out you get a similar compute architecture that is much more efficient from a rate distortion point of view. So much better performance in the end.
One of the key elements of the transformer-based transform coding paper is this idea of visualizing the effective receptive field. Can you talk a little bit about what that means and where it comes into play?
So, of course, knowing that you can obtain better performance using these transformer blocks is not enough. We also want to know why this is, so that we could potentially make use of it. So what Yang and Yinao did was visualize this effective receptive field. And how you could kind of view this is asking your network for a certain feature, what inputs do I need to change and in what way in order to maximize or minimize this feature. So you can just use the property that this network is fully differentiable and compute a gradient with respect to the input image. And so what they found was that for these convolutional models, if you look at their use across different compression tasks, the effective receptive field size was largely the same. So it was something like 30 by 30 pixels influence a local feature. But if they look at the results, the same results for the swing transformer-based models, they notice that in contrast, for tasks where the model only has to look at a single image, the effective receptive field was very small, indicating that you only need a bit of local information in order to compress efficiently. But when they applied it to a task where two images needed to be compared, so a motion estimation task for this motion compensation that we talked about for video, they noticed that the effective receptive field was much larger. And this makes sense from an intuitive point of view, because if you want to determine how across two frames a certain motion appears, you would want to look at a lot of context. You wouldn't want to look just at a very tiny area. So this kind of hints that these SWIN models are able to better determine how much information they should take into account from a local area in order to make their decisions.
When I hear the description of the effective receptive field, it makes me think a little bit about ideas like Lime, where you're kind of creating some perturbations in the input and you're trying to see how they flow throughout a network. Is it a similar idea?
It sounds sort of similar. Yeah, I think one major application, but that really is a blast from the past, is this deep dream style image generation, where you're kind of asking your network, okay, how should I change this input in order to make it resemble a dog or a cat or some concept? But of course, similar techniques have been used in many different settings since.
There was also some work in this paper that looked at the kind of characterizing the latent space. Can you talk a little bit about what that showed?
So Young and Yinao performed a couple of analyses, and some of which were aimed at seeing how these SWINT compression models utilize the latent space and whether they utilize it in a better way than the convolutional counterparts. And one of the ways in which you can show this is by looking at how many bits are being transmitted through every latent channel. So the latent space has a certain number of channels, and it also has some spatial dimensions. And for each channel, you can count how many bits are going to be spent in order to transmit the information in this channel. And when you order these channels by the number of bits, you can kind of construct a progressive decoding scheme. You only transmit the first channel, you get some of the key information, maybe you get the shapes right. Then you transmit the second channel, you get some of the details right, and so on. And it turned out that these SWINT models were able to distribute the information more evenly than their convolutional counterparts. So for progressive decoding style schemes, this is potentially interesting because it means that you can opt to, for example, just transmit the first half. You're guaranteed to get some information across. But it's also interesting in case of imperfect channels. So if some information is lost, let's say, could you resample these channels, or could you still decode something that looks like what you meant to decode? And so they have some experiments in the paper as well, where they mask certain parts of the latent channels and show that the SWIN transformer is more robust to this than the convolutional compression models, resulting in cleaner reconstructions, even if some of the information is missing.
It's occurring to me that as you've been using the word channel here, I've been thinking of channels like in an image sense, like color channels
Mm-hmm.
and things like that. But you're not necessarily using it in that sense here.
I guess it's similar if you look at input images as a tensor. Yeah, sorry for me. Whenever I think of images, I always see four-dimensional tensors: batch,
Uh-huh.
channel, height, width.
Yep.
And for this latent space, it's actually quite similar. There's also a
Oh, is
batch
it?
dimension, a channel dimension, and in this case, it happens to be a large number of channels because we choose it to be. But from a tensor perspective, it's the same thing.
Okay. But they don't necessarily correlate to a particular physical property like a color or something like that.
They don't know. Uh,
Yeah.
what we hope is that these transforms, the learned encoder and decoder, that they're able to map to some space where all of these redundancies are being squeezed out, but we have no idea what that space means inherently. We can visualize it, and there actually are some visualizations in the paper as well, where you can see some correlation to the original input and some spatial patterns appearing and so on. But there are no physical properties that you can tie it to now.
It sounds like it's not quite as clean as some of the early work looking at layers of CNNs and seeing the, textures, shapes deep, and then textures and things like that.
Yeah, I think for some channels you can trace it back to some properties, but there's no guarantee. And what we've seen is that this sometimes is highly dependent on the input image as well. So when you pass an image through it and you see some response, and then you think, hey, great, I found one that corresponds to grass. And then the next image goes through it, it also responds, and it's not a grass image. So sadly, we can't really tie it to any one property now.
To what extent does this work then kind of fit into some of the other things that you're doing? Like we alluded to some of the work on kind of intra-frame um, for video, and there's some other stuff that you've done that we haven't talked about, P frame and B frame codecs. And like, is the transformer based a new foundation piece that you then can kind of plug in all the other things that you're doing for video compression around?
Yeah, I would say so. I would say so. I think our team is working on many directions simultaneously, and that hopefully are complementary. So, like you mentioned, we have some work on different schemes for neural codecs, and this work really is aimed at replacing some foundational building block for any codec. So, what Yang and Yinhao did was not apply this just to image compression, but also did some feasibility studies that showed that it held promise in the video setting. And in this case, it was only aimed at how do you call it? Not streaming, but real-time video. So in low delay setting, it's referred to in the compression setting. But there's no reason that this could not scale to the streaming use case as well.
And what are some of the future directions that you're looking at in terms of building on top of this?
So I think, like you mentioned, scaling it to some of these other codecs that we've been building, the codecs that are well suited for the streaming case, for example, seeing whether we can reduce computational complexity further. And as you may know, we've been demoing some of our earlier codecs throughout the past year. And of course, it's interesting to consider whether we can actually make a feasible prototype out of this, something that would be runnable on device.
On that note, what kind of results did you see with from a computational perspective with these type of coding?
The convolutional ones are about equally expensive in terms of max, so multiply and accumulate operations. So it depends how you measure compute. From that point of view, Swin transformer models are somewhat counterintuitively more rate distortion per MAC efficient. So you get much better performance for the same amount of max. But there's a small caveat. The attention operation is memory hungry. And because of the softmax operation, even these Swin transformers, which only compute the attention in this local window, there's still a big hit to the total memory. And this is noticeable. And Yang and Yina also included some comparisons on things like peak memory usage, which showed that the convolutional model is still the least expensive one there.
So that is one of the papers that you and your colleagues are presenting at ICLR. There are a couple of others that I'd love to hear a little bit about. One of those is the Confess paper. Can you share a little bit about that paper?
So they're using contrastive learning in a cross-domain few-shot setting. So what this means is, for example, you were to train a model on ImageNet, and you want to use this in a setting where X-rays are being used. So it really is a big jump from domain to domain. And the method they devised sort of combines 3 steps in order to facilitate this domain shift and enable it. They do use self-supervised pre-training in order to create a certain set of features. Then they use a feature selection scheme where they sort of train a mask that is fit for a particular target domain. And they perform fine-tuning at the end. And it turns out that this 3-step procedure, of which the self-supervised pre-training is probably the most important one, you can easily transfer from domain to domain without overfitting on the very few test samples that you may have from the new target domain. So this is especially important when you think about use cases like personalization. Let's say you've trained a big model on a huge data set for many different users, and now you want to apply this to just your use case, then this few-shot learning becomes all the more important, likely because your data is expensive to obtain.
And how is self-supervision built into this?
So the first step of this process is mainly about learning a good representation. And so contrastive methods have generally been used in vision in order to build a certain set of features that could be used for many different tasks. So for many semi-supervised settings, for example, it turns out that self-supervised pre-training on large unlabeled data sets are a great way to kickstart the actually quite difficult semi-supervised process. So it's kind of a way to use large unlabeled data sets through self-supervision so that you don't have to go through the motion of obtaining this expensive labeled data set beforehand.
Another paper we wanted to talk a little bit about is the Steerable Cnn's paper. What does that mean? What's a Steerable Cnn?
I would say the best way to introduce it is to talk about these group equivariant nets that you've probably talked about with Taco Cohen some time ago. Normal convolutional models, they're equivariant to translations. So that means you shift the input, the output of the operator shifts with it. And what group equivariant nets are generally aiming to do is be equivariant to different symmetry groups as well, not just translation, but for example, also reflection, flipping. I mean, you've talked to Taco about this. So steerable CNNs are one of the most general ways to accomplish this. And what my colleague Gabriella has done in this work is a theoretical analysis of the space of these steerable filters and kind of come up with the parameterization for the space. And what this will do is if you're interested in building a network that's equivariant to some certain symmetry group, let's say one that's solely aimed at reflections and 90-degree rotations, then what you would have to do before Gabriella's work is kind of work out an architecture and a method that could allow you to satisfy the constraints of that symmetry group. But using their work, you sort of have a general, almost automatic procedure for deriving the steerable filters. And what's nice about it is that the code is open source. So anyone could use this and kind of kickstart building a steerable CNN for their symmetry group of interest.
Got it. So you have a particular type of symmetry that is expressed in your problem that you want to exploit, and previously you'd have to kind of handcraft a method for taking advantage of that. And it doesn't sound like it's a general mechanism, but rather a procedure that you would follow that leads to a mechanism that works for your specific use case. Is that the right way to think about it?
Yeah, I think so. Yeah, like you mentioned, most of the works on steerable CNNs so far have attacked a specific group. So, for example, working on globes, when you think about things like weather data, of course, they're not actually 2D. They operate on around the globe, around the Earth. And so it's desirable to be equivariant across that sort of space as well. And so what's previously been done is you kind of handcraft for this specific use case a set of steerable filters.
Awesome. Well, I'd love to have you share a little bit about what you're most excited about looking forward in the field that you're focused on, the neural compression and neural video compression. What's exciting that you see down the pike?
I think one direction that I'm particularly excited about is the whole perceptual quality direction. I really believe that this is where neural codecs shine, not just GAN-based codecs, but really any codec that's aimed at improving perceptual quality. But for example, with the advent of diffusion models, a different type of diffusion probabilistic models, a different type of generative model, again, very good at generating high perceptual quality details, but not exactly straightforward for using in a compression setting. We know that neural networks are able to generate these sort of plausible details, and trying to make use of that and trying to exploit that is something that I'm particularly excited by. And at the same time, I'm also excited about bringing down the compute and actually making practical codecs, things that that you or I could run on a mobile phone and watch videos with, because that really moves it from the academic setting to the tangible setting.
Mm-hmm. When you talk about the increasing the perceptual quality and incorporating different pieces like GANs, is it more often that you're kind of taking elements of these different types of models and building them into one kind of end-to-end train thing, or are there other cases where you've got kind of higher level components that you're bringing together into more of a system type of an approach to solving the problem?
There sure are hybrid approaches. I think the most elegant way is always this end-to-end approach, where you have an encoder that's a network, you have a prior model that's also a network, and the decoder is a network. And there are some, I think, really well-made work from the Google Perception group, for example, on an end-to-end image codec, which I believe they call high-fidelity generative image compression. And in this case, the decoder is a conditional GAN mapping from this latent space to image space. But the encoder is a network, and the prior is a network as well. You can train this entire thing end to end by mixing a few loss functions. I think it's quite an elegant way, but it's not the only way. And there definitely is something to be gained from also looking at domain expertise. In particular, when you think about bringing down complexity and making sure that you don't need a huge neural network in order to kind of rebuild or learn what other people have already figured out for you.
Right, right. And does that what are there clear lines from a kind of performance and efficiency perspective? In other words, like, is end to end always more computationally intense, more efficient, or does it depend on the specific set of architecture and implementation?
It's hard to predict where this will go. I mean, at the moment, most of these end-to-end architectures, they are computationally fairly expensive because they're kind of replacing many components that make use of inductive biases. And those inductive biases, especially when you think about standard codecs, they're often also aimed at bringing down the complexity, not just at obtaining the best rate distortion performance. So some innovations in more traditional methods, they may have been chosen over others, not necessarily because they are bringing out the very best rate distortion performance, but because they have good rate distortion performance, but are also efficiently implemented on hardware. So with neural codecs, especially end-to-end codecs, given that it's a fairly recent field, a lot of the focus has been on making models that scale well and making use of the compute we have. And recently, there's been a lot more attention towards making practical codecs as well. So, for example, with some of our demos in the last year, and recently, David Minnen from the same Google Perception team gave a keynote at ICIP, in which he also had a call to action, a look at models that are computationally less expensive, but still obtain good rate distortion performance. So I hope that answers your question. I think now end-to-end is still computationally fairly expensive, but we've shown that it's doable. You can do on-device decoding, but there is a change in the works, I would say.
Awesome. Well, Auke, it was wonderful chatting with you and learning a bit about all the things that you and your team are working on. And best of luck with your presentations at the conference.
Thanks, and thanks a lot for having me.